Yeah, so my demo will be fairly like very simple. I'll just motivate circle stocks like why circle stocks. So circle stocks, they are using something called as Mersenne primes. And they are of the form p equal to 2 to the n minus 1. And the reason why we use Mersenne primes is that field multiplication modulo, then after field multiplication, like reduction modulo prime is fairly simple in these Mersenne primes. So let's say we are working over the 31-bit Mersenne prime, so M31, and you need to compute a field multiplication. So this will be 31 bit and this will also be 31 bits. So the product will be 62 bits. So this X you can actually decompose into like, so these are the 62 bits of X. Which can be decomposed into the lower and the higher bits, each of 31 bits. And you can actually write this X as, so the lower bits plus 2 raised to 31 times the higher bit. And so you got the 62-bit result after the field multiplication. But now you need to reduce this modulo the prime. So for M31 the prime is 2 raised to 31 minus 1, the same form where n is 31. So now if you do like X, when you compute the reduction modulo prime, so X will be L plus 2 raised to 31 times H modulo 2 raised to 31 minus p, which is a prime. Now if you compute this term modulo 2 raised to 31 minus 1, this will be its value will be 1. So X will be L plus H mod. So after multiplying two integers and then reduction modulo prime is same as just doing a single field addition. So this is the 31 bit and this is also 31 bit, and you're adding to 31 bits modulo the prime, so it is just a single field addition. So actually in Mersenne primes the reduction modulo of prime is just a field addition, so that is why like they are very fast. And so that is why we want to use these Mersenne primes. We want to build our snarks over these Mersenne primes. And another fact of these Mersenne primes is that so for Mersenne primes, P is same as 3 modulo 4, and in the paper like they mentioned that this implies that X square modulo prime so if P is 3 mod 4, then this implies that X square equal to minus 1 modulo prime. It has no solution. So I just want to go through like why is this, like what is the insight behind this implication. So you could actually prove this using proof by contradiction. So you can write this as, so P will be of some form 4k plus 3 for some integer k, and let's say you raise both the you raise this let's say like you assume that there exists an x such that x square. So we are doing proof by contradiction. So let us first assume that there is an x such that this expression holds, and now you'll raise this expression, the left hand side and the right hand side, by so raise both sides by p minus 1 by 2. Then the expression on the left hand side will be it will be x raised to p minus 1 by 2, which will be same as x raised to p minus 1. And here like you can use the Fermat's theorem where a raised to p is equal same as a mod p. So x raised to p minus 1 will be same as 1 modulo p. Whereas when you calculate the RHS, it will be minus 1 raised to p minus 1 by 2. So you can use this expression to compute p minus 1 by 2, where p minus 1 by 2 will be 2k plus 1. So using this expression, I'll just use. So you just subtract minus 1 and divide it by 2, you will get 2k plus 1. And this, if you see, so it will be something as minus 1 modulo p. So this is where we get a contradiction, where on the left hand side you get 1 modulo p, and on the right hand side you get minus 1 modulo p. So our assumption was false, that there exists an x such that x square is minus 1 modulo p. So basically the polynomial x square plus 1 has no roots in FP. Yeah. So so this was one of the fact which was covered in the paper regarding Mersenne primes, and like, so I just wanted to like give a brief overview on why this fact holds. Yeah. So yeah, there is no root for the expression x square plus 1 in FP, but what we can do is that we can use field extensions. So we can extend this FP, we can have a quadratic extension of FP where there will be a solution to x square plus 1 equal to 0 mod p. So yeah, so yeah, in statistical structs we use this field quadratic extensions of FP. So this was like an aside, and coming back to like motivating like why circle structs. So we want to use circle structs because they are very fast, but the problem with circle structs is that, the problem with using Mersenne primes is that they are of the form p equal to 2 raised to n minus 1. So if you see the order of the multiplicative group, it will be 2 raised to, it will be p minus 1, which is 2 raised to n minus 2, and this does not have a large this does not have a subgroup which is a large power of 2, and we need that subgroup. So we need a large power of 2, like a factor like 2 raised to k, and we need this large power of 2 because we need a large power of 2, a domain of size large power of 2 to compute the FFT for Frey based polynomials. So to overcome this issue, we work with, like I said, we work with quadratic extensions of FP, where we are working with FP square. So the size of FP square will be like P square, and the size of the multiplicative group will be P square minus 1. And here, like, we could write this as P plus 1 times P minus 1. So the multiplicative group FP square star, it has a subgroup of order 2P plus 1, and if P is the Mersenne prime, then this the size of this subgroup is same as 2 raised to n. So and this in fact is our circle group. Is the circle group over which we do the circle FFT. So yeah, I mean, having a quadratic extension of FP will give us a subgroup of size 2 raised to n, which will and this order of the group P plus 1 is in fact our circle group. And in my next demo, I'll go through the group structure like of the circle group. Yeah. So that was like a short motivation behind circle structure.
My question that is yp equals to 3 mod 2, and then you have that conclusion x squared equals to
this
1. Yeah.
Yeah, so that is what I was trying to explain here, because
I mean, so they are equal. I mean, why this? You have this, then you.
Yeah. So this is like if P is 3 mod 4, then x square plus 1 modulo P has no solution in FP. So this is like if then, like this is like you could say this is a lemma, and then I've tried to prove this lemma using a proof by contradiction.
Oh, I see.
So if this expression holds, then this has no solution, and that is the lemma, and this is like a proof by contradiction.